Imagine you are trying to tune a complex engine. You want the perfect mix of fuel and air, but you cannot test every combination by hand. In deep learning, this is exactly what we face when we try to find the optimal parameters for a neural network. We call this hyperparameter search, and it is notoriously expensive. Every single trial requires training the entire model from scratch. When you multiply that by dozens of datasets, the computational cost explodes. Most engineers try to solve this by making the training process faster. They look at frameworks like PASI, which stands for Parallelization Strategies for Efficient DNN Training. This system uses dynamic programming to discover how to split the model across different machines. It is brilliant for making a single training run faster. However, it does not solve the problem of finding the right settings in the first place. There is a significant gap in the literature here. Most papers focus on parallelizing the training itself, not the search for the optimal parameters. We are left without a concrete methodology for distributing the search load efficiently. Here is the thing. The search phase is fundamentally different from the training phase. During training, the data flows through the network in a fixed path. During search, every trial is an independent workload. You are not training one model, you are running hundreds of training jobs simultaneously. This means we should leverage task-level parallelism. Think of it like a construction crew. You do not ask every worker to build the same wall. You assign different tasks to different teams. In our case, each team handles a different set of hyperparameters. Now consider this. If you have a limited number of graphics processing units, how do you manage them? If you simply throw all the jobs at the hardware at once, you will hit resource contention. The system will grind to a halt as machines fight for memory and bandwidth. A fault-tolerant distributed search pipeline is required. This pipeline must dynamically allocate compute across heterogeneous datasets. Some datasets are small and fast, others are massive and slow. A static allocation strategy will fail here. You need a system that knows when to start a new job and when to wait. This is where the concept of dynamic resource allocation becomes critical. The orchestrator of this pipeline acts like a traffic controller. It monitors the load of every node. If a node finishes a job early, the controller assigns the next task immediately. If a node is struggling, the controller pauses new assignments there. This prevents the bottleneck where one slow dataset drags down the entire search process. It ensures that the hardware is utilized at maximum throughput. The controller must be smart enough to detect when a node is idle and when it is saturated. Another crucial element is early stopping synchronization. You do not want to wait for a full training run if the model is clearly not learning. In a parallel environment, this is tricky. If you stop one job, you must ensure the search continues smoothly without losing track of the best parameters found so far. The pipeline needs to communicate these results back to the central controller instantly. This allows the system to prune unpromising branches of the search tree. It saves massive amounts of compute power that would otherwise be wasted on models that will never work. Research into sparsity-aware and cyclic data parallelism strategies offers further insights. These methods reduce communication overhead during hyperparameter sweeps. They are more efficient than standard synchronous data parallelism for large-scale searches. By understanding the sparsity of the data, you can predict how much compute a specific dataset slice will need. This prediction helps the dynamic allocator make better decisions about which job goes where. It allows the system to prioritize smaller, faster datasets while batching larger ones to keep the pipeline full. Modern distributed training frameworks suggest that combining model parallelism with data parallelism is essential for scaling. But for hyperparameter search, the priority is maximizing throughput. You want to run independent experiments concurrently on available hardware slices. This is supported by discussions in libraries like scikit-learn. Parallelizing grid search across slices of data or parameter combinations yields higher throughput than sequential execution. The underlying training infrastructure must support concurrent job scheduling without resource contention. As we look to the future, automated hyperparameter optimization will increasingly rely on these dynamic resource allocation strategies. The parameter spaces are growing exponentially. We cannot rely on static grid searches anymore. We need adaptive, parallelized search strategies that can handle diverse datasets without incurring prohibitive overhead. The goal is to move from a system that waits for the slowest job to a system that adapts to the fastest available resource. Ultimately, the challenge is not just about speed. It is about reliability. A distributed search pipeline must handle failures gracefully. If a node crashes, the pipeline must reschedule the job without losing progress. This fault tolerance is what separates a theoretical solution from a practical one. By focusing on resource contention strategies and early stopping synchronization, we can build a system that scales with the complexity of our models. Thanks for watching all the way to the end. I am a one-person team working hard to make each video better than the last. Subscribe if you found value. It is the best way to show support. Drop a comment with your biggest takeaway. See you in the next video.